Ever wondered what happens when you decide to flex your muscles? Today, we explore the fascinating world of neurobiology, diving deep into the intricate process of muscle contraction and neural signaling. It all starts with the basic building block of the nervous system, the neuron. Picture a neuron as a tree, with branches called dendrites, a trunk referred to as the cell body, and roots known as the axon. When a neuron receives a signal, it undergoes changes in its membrane potential, triggering depolarization or hyperpolarization. These fluctuations, known as graded potentials, can either increase or decrease the neuron's electrical charge. Imagine a row of dominoes. If the changes are strong enough, they can cause a cascade, leading to the threshold being met. This initiates an action potential at the axon hillock, which then propagates along the axon, much like dominoes falling in a line. Our neuron is now ready to communicate with the muscle cell, or myocyte. Picture the end of the neuron as a bulb filled with tiny vesicles containing a chemical messenger called acetylcholine. This synaptic end bulb is separated from the muscle cell by a tiny gap known as the synaptic cleft. Once the action potential reaches the end bulb, calcium ions rush in, causing the vesicles to fuse with the membrane and release acetylcholine into the cleft. The acetylcholine then binds to receptors on the muscle cell, triggering an influx of sodium ions and propelling an action potential along the muscle cell membrane, or sarcolemma. Now, let's shift our focus inside the muscle cell. Picture a network of tiny tubes called the sarcoplasmic reticulum, filled with calcium ions. The action potential travels along the sarcolemma and into the cell via T-tubules, prompting the release of calcium ions. These calcium ions bind to a protein called troponin, which is attached to another protein, tropomyosin. This binding causes tropomyosin to move, revealing myosin-binding sites on the actin filaments. The myosin heads then attach to these sites, pulling the actin filaments towards the center of the sarcomere, a process known as the power stroke. But what happens when we want to relax our muscles? The motor neuron stops releasing acetylcholine, causing the muscle cell to repolarize. Calcium ions are pumped back into the sarcoplasmic reticulum, and tropomyosin re-shields the myosin-binding sites, preventing further contraction. And there you have it, the intricate ballet of muscle contraction and relaxation. From the dendrites of a neuron to the myosin heads in a muscle cell, it's a finely tuned process that happens in a split second, every time you flex your muscles. Remember, it starts with a neuron receiving a signal, leading to an action potential that triggers the release of acetylcholine. This chemical messenger prompts an action potential in the muscle cell, causing calcium ions to be released. These ions bind to troponin, revealing myosin-binding sites and leading to muscle contraction. When it's time to relax, the process is reversed, and the muscle cell returns to its resting state. In the grand dance of life, every twitch, every flex, every movement is a testament to the marvels of neurobiology. So, the next time you decide to flex your muscles, spare a thought for the intricate processes at play.